Hello everyone, good evening. Welcome to the week 2 live interactive session for Advanced Computer Networks course. So I am recording this session. Hope it's fine with everyone. Maybe we'll wait for 2-3 minutes more and then we'll get started with the session. Can someone please confirm if I'm audible?
Yes, you are audible.
Thank you. Yeah, so let's get started. Hope the screen is visible. So, in the week 2, majorly the portion covered in professor's lecture was basically on how the routing table is designed so that the performance requirement of fast lookup, low memory and all is taken care. Okay. So before getting into like how the routing table is handled, the data structure used, the different approaches discussed was one was a binary trie-based approach, then optimizing that trie-based routing table like path compressing, multi-bit trie, all those things. One common thing that is discussed or dealt is something called as prefix, right? So before getting into the try and all that, let's see what a prefix is. I'm not sure how many of you are aware of it. But I'll just quickly take one or two example and tell you what is meant by a prefix. Okay. So let's take an example. of an IP address like 245.10.10.10. Okay, this is actually an IP address assigned to, let's assume this is an IP address assigned, and let us see what will be the prefix given the CIDR representation of an IP address. Okay, so assume that the address is 245.10.10.10 and the prefix length or the network mask length is 26. So by 26, we mean that 26 bits out of the 32 forms the network ID, and the other um, 6 bits is used to identify the host ID. One second. അജി ഇവിടെ കൂട്ടാജി സെഷനാ എനിക്ക് വാതിലടയ്ക്ക് വാതിലടയ്ക്ക്. Yeah. So now, given this address and the length, how do we identify the prefix? So it's actually very simple. When we say this 26 is the prefix length, using this prefix length, we can actually arrive at what is known as a subnet mask. Subnet mask is nothing but all the bits corresponding to the network ID fields will be 1. So here 26 bits corresponds to the network ID, right? So 26 bits will be 1. The recorded session actually it will be shared by the NPTEL team, okay? But somehow I don't see that link updated in the NPTEL ACN course site. Maybe normally we actually upload this recorded session in YouTube, and we update this particular the YouTube link in a sheet, and that sheet actually gets shared across to you. All the slides, this handwritten notes, everything we put it in a drive, and the drive link also actually is kept in a sheet, and normally that sheet is what NPTEL used to share it across with the students. But I don't see that link shared for ACN. So probably I'll once check with them and get back. For the drive, I can share the link by the end of this session. I'll share the drive where I'll be putting these PPT and also this handwritten notes. Hope that clarifies. Okay, so this is what is 26-bit network mask means. So the 26 bits out of the 32 will be 1 and rest of the 6 will be 0. So to get the prefix length, what we do is we actually, so this is also called a network mask. So what we normally do to get the prefixes, we do an AND IP address. We do a symbol AND operation with the network mask. That will give you the prefix or the network ID. Okay. So in this scenario, 245 is 1111 dot 10 is 1010 dot. So, okay. So of this, we are actually doing an AND with this, right? So all the first 26 bits will remain as such. So the prefix will be to either I can write it as 245.10.10.0, or this part we will ignore and we'll put a star over here. We'll ignore this part and put a star. Okay, now what if it is 245.10.10.10/4? What will be the prefix? So 245, so 4, if 4 is the prefix length, then what will be the subnet mask? Mask will be 11110000. Only 4 bits will be 1. Rest of all the bits are zeros. Or 0.0. So of 245 is 11110101 dot 10 dot 10 dot 10. So this will form the prefix. So prefix will be 1111 star. Okay. Now if it is like /16, if I give 245 dot 10 dot 10 dot 10 /16, what will be the prefix? Prefix will be 16 bits will be 1, which is nothing but this one. So it will be 11110101. Further will be star. Okay. So I just thought I'll just quickly tell you, because all through the discussion we'll be referring to what is known as prefix. So now I think we'll get back to the try related discussions. Okay. So majorly the assignment questions were also from the try related things that was discussed in the week 2 lecture. So I'll also try to solve some of those related problems, so that will help you with the assignments. Okay. So basically what try is a software implementation. In software, if you are going to implement the routing table, we typically use this data structure called try. We can implement the routing table in a software or in the hardware, or using special purpose ASICs also. Okay. So we'll start with if we are implementing it in software, what is the best way to implement, what is the best data structure to implement it, and then what are the optimizations possible. Okay, so the data structure that we normally use to implement IP routing table is typically a binary try. Okay, so let's see what is meant by a binary try. It is basically a tree-like sex structure, which will have all node will have 2 children, and that is basically the meaning of binary. Every node will have 2 children, and in case of since we are dealing with IP address prefix, which are represented in zeros and one, left will have normally in binary try structure, the left path is represented by a 0 and right is represented by a 1. Okay, now let's take some couple of examples and see how the routing or the try is formed given a certain number of prefixes. For example, let us see prefix. These are examples from Sir's lecture only. In case if you have any doubt, you can ask. Okay. P1, and this is the next stop. P2, 0 star. Next stop is 2. P3 is 1 star. Next stop is 2. P4 is 0 star. P5 is 1 star. P6 is 1 star. P7 is 1 star, and P8 is 0 star. Okay. So how do we, if I am given such a prefix, how do I construct the try that can be used for routing table lookup? So what actually happens is the routing protocols will run and they collect how different destination networks are reachable, and we call that information as routing table. Okay. So routing table typically comprises of how different destinations can be reached. It will contain the next stop information and the typically the port over which the packet has to be forwarded. Okay, so when we have this routing table and when a new packet comes, we actually need to look up the table and find out where exactly the packet need to be forwarded. Okay, so this prefix information, we can assume that this is what we get from the routing protocols. Now we have this information. Now we need to construct the routing table so that when a new packet comes, we can do a lookup and then we can correspondingly forward the packet. Okay, so let's see how this routing table is constructed. So when this star means it's equivalent of a default route, that is if I don't find any matching entry for a particular packet where to forward that packet, then this is the port to which I need to forward. So default entry is nothing but a wildcard entry. Everything will match to it. Okay. So the first entry will be star. Then we have 0 star and 1 star. So being a binary tree, left is 0, right is 1. So this is when there is a 0 followed by anything is a P2 prefix. So here we will have P2 and here we will have P3. Now P4 is 0 followed by again one more 0. So this is P4. P5 is 1 followed by another 1. So this is P5. P6 is 1, 1, 0. This is P6. Sorry. 1, 1, 0. That is P6. Now P7 is 1, 1, 1, 1. 1, 1 is there. Another 1 followed by another 1. So this will be P7. So when we write P7 here, suppose an input packet comes and with a prefix of 1111. For example, okay, I'll come to that once we complete the try construction. P8 is 0, follow 8 zeros, 1, 2, 3, 4. Okay, so this is P8. Okay. Now, suppose we have we have already seen this particular IP address, right? 245. Now we got a packet. So now we have our routing table. So this is the routing table represented in the try form. Now, if a packet comes with a destination IP address 245 dot 10 dot 10 dot 10. Okay. What is the start prefix of this? 1111. 0101 and it goes. Okay. So what will be the best match possible for this particular IP address? We will start from this corner, from this end, the 11 end. So it is 11111111. So then further on anything. So P7 is actually 111 star. So any sequence of ones and zeros after this first four ones will actually match to this particular entry. So our IP address 245.10.10.10 will match to this prefix P7. So in this prefix we will also have the information of where to forward this packet. So based on that, for example, I was writing here no the next hop information. So for P7 the next hop information is 3. So when a packet comes with this destination, it will go to the routing table. It will see, okay, 1, 1, 1, 1. This is the best match for this particular IP address. So P7 is the matching prefix. The next hop is 3. So this packet needs to be forwarded on to port number 3. Okay. So this is actually how the how the try will be used for lookup. Okay, maybe a couple of more examples. Okay, another example. P1 is 0011 star. P2 is 1001 star. If my voice is going low, let me know, okay? P3 1100 and P4 1101. So again, we will start from the root. So we start, okay. So there is no star, so there won't be any label or prefix attached to the top node. So first one P1 is 0, 0, 1 and 1. 0, 0, 1, 1. And further on, whatever comes, this it will match with this prefix. So this is where P1 is. Now P2 was 1, 0, 0, 1. This is P2. P3 is 1, again 1, 0, 0. This is P3. And P4 is 1, 1, 0, 1. This is P4. This is one another try. Okay, so like this you can, if the prefix is given, we can construct the binary try. Okay, so one of the issue with this binary try is if the it actually wastes a lot of space. The number of what to say, the comparisons that one have to do will be equal to the largest prefix given in the table. Somebody raised hand. Yeah. Okay. So, for example, in this first, this one, if you see, there is a skewed tree here, right? This is actually, there is a skewed tree which actually wastes a lot of lookup and time unnecessarily. If for example, if we got a IP address which have like 8 zeros followed by some okay, this is 0, 0, 0, 0, 0. This is was not needed. Okay, only 6 is there. 6 zeros followed by some number, for example 2 dot 10 dot 10 dot 1 or something. So it has to come here, 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 here. It is all a single line. Instead, if it was possible to keep all these 0, 0, 0, 0 here, these many comparisons in the in all of these nodes can be avoided. Okay, so to improve the performance, there is this optimization called as path compressing. So when we have such skewed child in the try, we actually compress them and take all the bits together and keep it in a single node so that we can reduce the overall height of the tree. So that is called as path compressing. Maybe we can see one or two. Is the try creating the try from the prefix clear with everyone? Do you want me to see some more examples before going to path compressed try?
Ma'am,
Yeah.
once again repeat பண்ணுங்க மேம் புரியல கொஞ்சம்.
Okay. What I meant was before going to path compressed try, shall I take few more examples of prefixes and show how the binary try is constructed? Shall I do that, or you all are familiar with it?
Ma'am, give more examples, ma'am.
Okay, all right. Maybe two more we can see, quickly see and then move to path compressed one. Okay. Yeah. Another example is sorry, P1 is star, P2 is 1 1 0 star, P3 is 1 1 1 1 star, P4 is 0 1 star, and P5 is 0 1 0 1 star. So when we start, so first we will see, okay, there is a wild card star which will match with everyone. So that will be the first entry, and P1, that will be the first entry in the try. Then let's take the next entry. One by one we will take and we'll just construct, go to, if it is a 1, we'll go to the right of the node. If it is 0, we'll go to the left of the node. So here the prefix is 1 1 0. So 1 is right, there is this node. Then again there is a 1 1, and then there is 0. So this forms it. Now further on, if anything comes, you can map it with P. Okay, sorry. This is 1 1 0. 0 goes to the left. Okay. So this is P2. Now P3 is 1 1 1 1. So we already have 1 1. Again, one more 1 here and one more 1. And this is this prefix, this is P3 prefix. Okay. Now P4 is 0 1 star. So P4 is 0 1. So first one is 0, then 1. So this is P4, and P5 is 0 1 0 1. 0 1, again a 0 and a 1. This is P5. So if you see, we can traverse this if you want to. If anything, if an IP address comes with starting with 0 1 0 1 1 1 0 0 dot x dot y dot z. Okay. So what it will do is it will start from this one. First is 1. Okay. Okay. That's okay. 1. Then it will see 1, it is 1, right? Now 1 followed by 0 is there, it is not there. So what was the best match this prefix got? It is P1 only. There is no other better match here. So it matches with P1 only. Now let me just change this slightly so that it will match with P5. 0 1 0 1. Okay. Now if this is the prefix, then we will start. What is the first one? First is 0, so it will come here. Then next one is 1, it will go again, traverse it. Then again it is 0, go traverse here. Then come here 1. After that we have a 1, but there are no more children for P5, right? So this particular IP address have matched this prefix. And if the next hop corresponding to this prefix is like 5, this packet will be forwarded to port 5. Okay. So this is how we construct the try. Maybe one more example. We'll wind this up. Another example. Mm, okay. P1. P1 is 0 0 0 0 1 star. P2 is a lot of noise is there when I'm speaking.
Hi. A bit noise is there actually. I think that mic is more near to the mouth.
Okay, because when I leave it, the volume is going down.
Oh,
Okay. I mean, let me know if this is fine.
yes, now it's fine.
Okay, okay. Maybe I'll talk little loudly. That's better. So P2 is 1 0 0 1 1 star. P3 is 0 0 1 0 1 star. P4 is 1 0 0 1 0 star. P5 is 0001 star. P6 is 101 star. Okay, now let's start the construction. So we have, there is no star prefix here. So the initial node will not have any prefix associated with it. So we'll have a 0 here, then followed by, so P1 is 0. Okay, let me make it little small. 0, followed by 1, 2, 3. 1, 2, 1, 2, 3, 0. One more 0, followed by a 1. That is P1. Right? 0, 0, 0, 0, 1. 0, 0, 0, 0, 1. That is P1. Now P2 was 1, 0, 0, and 1, 1. So you can see that whenever a 0 come, I take a branch to the left, and when there is a 1, we take a branch to the right. Okay, that is P2. That is 1, 0, 0, 1, 1. 1, 0, 0, 1, 1. Next P3 is 0, 0, 1, 0, 1. 0, 0 we already have. Then followed by 1, we take a right. Again 0, left. Then again a right. 0, 0, 1, 0, 1. 0, 0, 1, 0, 1. That is P3. Now P4 is 1, 0, 0. 1, 0, 0 we already have. 1, 0, 0. Followed by 1 and another 0. Okay. This is P4. And P5 is 0, 0.
Excuse me, ma'am.
Yeah.
Ma'am, 100. Oh, 1 goes to the right side only, ma'am.
Oh, okay. I think I made it wrong. Oh, okay, okay. 1 goes to the right. Which one I got it wrong? P2. Okay.
P2, ma'am.
1,
That
0, 0.
P4, ma'am. 1001.
Both will be wrong. Right. I'll draw it again. Sorry. Thanks for correcting. Okay. So P2 is 1 followed by 2, 0. Then followed by, right? Correct?
Ah, yes, ma'am.
Right. P3 was 0, 0, 1, 0, 1. That is correct. P4 is 1, 0, 0, 1, 0. That is P4. Now P5 is 0, 0, 0, 0, 0, 0, and 1. P5. And P6 is 1, 0, 1. Okay. Now, if I want to add, maybe let's add 2 more prefix to it. P7 as 0, 0, 1 star. P8 as 1, 0 star. And P9 as 0, 0 star. Let's see how it comes. So P7 is 0, 0, 1. 0, 0, 0, 1. So we have this. So we will mark this as P7. Now P8 is 1 followed by 0. So we already have that. We'll just mark it with P8. P9 is 0 followed by 0. 0, 0 and another 0. 1, 2, 3. So this is P9. So this is how we construct a trie. Now maybe tell some IP address example. We can see if we can look up this. Maybe the first one of that alone. Okay, 192. You should tell me the 192 is 128 plus 64, right? 1100. Is it so? Right? So I think so. 192 was. Yeah, so the prefix will be 1100 followed by 0000. So let's see if we have such a prefix. Oh, we don't have such a prefix. One we have. After that, we don't have a prefix. So it will come here. Okay. So there is no prefix associated with it. So there is no route for this particular IP address because we don't have the wildcard entry also. Okay. Any other IP address which maybe we can try mapping? 1001 followed by what is this number? Okay, if this is the prefix, if this is the prefix 1001 followed by 0000, 1001. Okay, let me make this also. Yeah, it would be very helpful if you could give me the decimal. I mean, sorry, binary. We'll take that 172. Okay, let's see this example 1001 1000. Okay, if this is the prefix, then first it will come 1 0 0 1 followed by 1. So it will this IP address, the IP address with this will map with this P2, and the next hop or the port corresponding for that particular prefix will be used to forward the packet. So 172, what will be the 127 is like 0 1 1 1 1 1 1 1 1, right? So 0 0. So we don't have any prefix matching this. So this packet will be dropped. Yeah, fine. So 0 1 1, yeah, that I think we just checked 0, and after that we don't have any prefix matching it. So and here we don't have a wildcard also, so there is no prefix associated with this 0 star. So there is no prefix available, right? That is, there is no routing entry available for the prefix, so the packet will not be forwarded. Okay, now 172. 172 is 10101100. Okay, so let's see if we have 1, we have 1 0, we have 1, but further it is not there, but we have a prefix for 101. So this will match with P6 and it will get forwarded to the port corresponding to P6. Okay. Hops means, for example, if a particular, we are sending a packet from a particular host here, okay, and this packet is going through multiple routers, and then finally it reaches the destination. So all these from here to here is one hop. This is another hop. This is another hop. This is third hop, fourth hop, fifth hop. Just imagine jumping across. The packet jumps from this host to this router, from there to another next router. From here it again jumps to this router, jumps to the next one, like that. Okay, that's basically it gets forwarded from across multiple routers before it reaches the destination. I think now we can go to the path compressed try. This is an optimization done. Okay. So in case of path compressed try, what we do is, for example, if we have a, let's take a simple example. If we have a try like P1 and there is a 0 and there is a 1, P2. Okay. So if we have such a simple try like there is this from P1, if a 0 comes, then there is no option for for another 0. There is no entry available, right? What is available is only for this one. So when only such paths are available, that is when the intermediate node does not have two children. When the intermediate non-prefix node does not have two children, that is it have only single children, then we club this to compress this two and make it to 1. Okay, so what will happen is P1 and 0. Here P2 will be written, and in addition to that we will also tell the compressed information. So how many length we have compressing. We are compressing only one bit, right? This 1 0 and 1, it was like this, right? 0 and 1. Instead we just made it a single and that. So how many bits have we skipped, or how much is the skip length that we are skipping? We are skipping the height of the tree by 1. So we will also mention the length by which we have compressed it, and also what is the bit that we have compressed in. So the bit here will be, it is called the skip segment. Segment is 0. So sorry, this not 0, 1. Skip segment is 1. Whatever corresponding to this path, we have compressed it and taken it over here, and we mention it here. So this is what is path compression is. Another example will be, so we can also write it as P1, P2. Instead of 0, you can write 0, 1. Right. So this try is equivalent of accepting a prefix of wildcard or 0, 1. So the same will be done by the compressed try also. Same routes, destinations will be accepted by the compressed try as well. Another example is P1, 0, another 0, and P2. So here again we can compress this to P1 and P2, 0, 0, 1. So here the skip length is skip length is 2. So this 2 we have compressed. Skip length is 2 and the segment is, oh sorry, how do I write 0, 0, 1? Actually 0, 0, 1. Should I write it the other way or this which direction? Fine, normally we'll write this way only, no? Okay. 0, 0, 1, and the skip length is this one, 0. I mean 6 segment is 0, 1. This one followed by this, okay? So that was another example. Maybe we'll see one little longer example. So here there is a P1, there is 0, another 0, which is, this is P2. Okay. Then this is 1, P3. Then again 1, 1, 1, 1, 0, P4. Okay. P5. Okay, now can you tell me which all we can compress? Can we compress this path P1 to P2 0 path? We can compress, right? There are the intermediate nodes does not have two children, right? So we can compress this path. So P2 will come over here, and the segment skip length will be 1, and we are compressing it by 1, right? Clubbing the 0 and 0 to a single 0. Then another thing that we can compress is here it has two children. So this node we cannot, but this node we can compress. Here this is this node only, and plus this P3 also we can take it up. This is an intermediate node which does not have any children. So this P3 we can compress up, P5 we can compress. Okay, let's try how it comes. So P1, P1, 0 only, we will write P2, and what is the segment is 0, length is 1. Okay, or you can even write 0. That's not an issue. Okay. So 0 we have kept it together. So so when we do a path compression, what happens is in binary trie we have seen that all the nodes have comparison of one bit is happening. We are only checking whether it is 0 or 1, 0 or 1. Only one bit comparison is happening. But when we do a path compression, so the number of comparison, the bit comparison actually now is variable. So sometimes if we skip by 1, if the skip length is 1, then comparison becomes 2. If the skip length is 2, the number of bit comparisons done at a particular node becomes 3. So it actually varies. So variable comparison happens in path compressed tries. So here we will skip 1 and 1, 1, 1, and we will make it P3. Then since this intermediate child have two children, we cannot skip, we cannot compress it. Then here there is one scope for compression. So we can make it 1, 0, and we can make it P4. And here this is 0, 0, and we can make it P5. Right? Oh, in between I missed the other note, sorry. P3 is here, then this person is there. Okay, there we do the further compression 1, 0, P4 and 0, 0, P5. This node we cannot compress because it have two children. Okay, so this is how we can reduce the height of the tree. So now earlier what was the height of the tree? 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. Yeah, the maximum number of worst case scenario, the maximum number of comparison or traversals that had to be done was 6, whereas now it is 1, 2, 3, and 4. Okay, so using this technique, we tried to actually reduce the height of the tree, and thus reduce the number of operations that needs to be performed. So that was one example. You can see one more example. Are you able to follow? Any doubts?
Yes, able to follow.
Yeah. We'll see one more example, then we'll go to the next optimization technique. Okay. So here the prefix P1 is star.
Hello.
Yes.
Yes, ma'am. Um, for what reason we are compressing this one notes, ma'am?
For reason.
Yeah.
Like the agenda of this live interactive session is to help you with the problem solving, specifically for the weekly assignments. Okay. So the assignment questions are basically from these topics, right? So accordingly, I'm just taking couple of examples and trying to show how the compression is done. We'll also see how the multi-bit trie is formed, and then the last one discussed. I mean, is this what you are asking or anything else?
Okay, ma'am. Yeah. Yes, so
This basically videos are already there. So the session is problem solving sessions, right? So that's the reason normally we go with some examples and show how it is done instead of going through the theory part,
okay, ma'am. Thanks.
right? Okay, so first let's construct the trie corresponding to this prefix and then we try to compress it. Okay, so the first node here we have a wildcard prefix which will match with everyone, any destination. So we will have that as first. Then it is 1 star P2. Then we have P3 which is 0 followed by 0 P3. Then P4 is 1 0 1. P5 is 1 1 1. P6 is 1 0 0 0 1 0 0 0. P6. P7 is 1 1 1 followed by 0 and a 1. And P8 is 1 1 1 followed by 0 0 1 0 0 1. Sorry. P9 is 1 0 0 0, one more 0 followed by 1 and 1. That is P9. Okay, now let's try to compress this trie. So here we know we can have a compression done here. There is a intermediate node which have only one child. So there is a compression possible here, and the skip length here will be, instead of 0 and 0, we will make it a single child. So it will be skip length will be 1. Here there are 2 children, not possible, single child. This is a intermediate node with a single child. We can compress here. There is a 2 are there. This is a intermediate node with a, this is not possible, and here we can have a compression. Here we can try a compression, path compression. Okay, so this is how we identify. So basically, we're doing it to reduce the height of the track. Okay, so now I'll take another example question from the last year's assignment. Yeah, the question is yeah, so there is a prefix given. This is given in the last year's question. P1 is star, P2 is 0 star, P3 is 1 star, P4 is 1 0 star, P5 is 1 1 1 star, I didn't get that. Sharif, you can unmute and talk if possible.
Ma'am, I said value of P1, P2 is higher to lower. Can you make an example?
Value of P1 to P2 higher to lower. No, I am not getting it. Sorry. I'll come back after this question.
Ma'am, I'll asking you P1 to P3, P4 is ma'am.
Huh.
Is changing the value multiple is one or two through three, two digit, four digit, two will change it then, ma'am. Can you get an example?
For example, are you asking like in P2 currently in this example?
Is three digit and P3 is two digit, then
Oh, that should not be
that's
a
like
problem. Yeah, that's not an issue. We can do it. So we can
that's
that
it's ma'am.
that
That's why I'm asking you, ma'am.
no that whatever it be in whichever order you write, end of the day the try will be the same. Whether like for example, if I keep P6 instead of P3, if I this is what you are asking, no? If I do it like
Yes,
this,
ma'am. Yes, ma'am. Yes,
right?
ma'am. Yes, ma'am.
It will not change. Try will not change, no?
Oh,
So I will
thank you.
not change you. If you want, we can just quickly. I'll show that. Okay, let me just finish this example and I'll show. Try will not change irrespective of the order we construct it. For the given prefix, whichever prefix you take first, like we can even start from P9. Okay, it's not like always we have to start from P1. We can start from P9. So like 100 like that, and finally whichever order we put the prefix and the final try will be the same. Oh, that clarifies the question, right? Yeah, so let's construct this try and do the compression. So first is okay, let's start from P9. Okay, not no issue. So we'll do this. 1, oops, 1 followed by 1 2 3 4 5. 1 2 3 4 5 0, 0, 0, 0, 0. Okay. Then 1. This is P9. Now P8 is 1 followed by 1, 2, 3, 4, 5, 0. 1, 2, 3, 4, 5. This is P8. P8. Now P7 is 1, 1, 0, 0, 1. This is P7. P6 is 1 followed by 3 zeros. 1 followed by 1, 2, 3. So this is P6. P5 is 1, 1, 1. P4 is 1 followed by 0. This is P4. Then P3 is 1. P2 is 0. Okay. Okay, so there is no compression possible here. Can we have a compression here? Can we have a compression here? Can we have a compression here? Okay, let's try. So it is 0. Okay, we have, okay, I forgot P1, right? So we will have P1 as such. P2 also will be same. There is no compression possible there. Then P3, it's there. Here there is no room for compression. So P3 to P5, it will remain the same. 1, 1, P5. Okay, because there was a this intermediate node have two children, so we cannot compress. But all these nodes have only one children, so there is a compression possible here. So we will bring P7 over here with a compressed segment length of 2. Okay, so here we will have 0, we will have P7. The segment, what is the segment that we compressed? We are compressing 0 and 1. Okay, 0 and 1 is the compressed segment and length is 2. Then here P4, P3, so here this P4 will be there, 0. Then there is an intermediate node which doesn't have any children, so we can compress this P4 and P6. So the segment length here, compressed segment length is 1 and the compressed bit is 0. So here it is P6. The segment length is 1, segment is 0, segment length is 1. Now again from P6 to P8 we can again compress. Again it is 0 and 1. So the segment that the bit that we compressed is 0 bit. So 1 bit we have compressed. So the length is 1. And then P9 will be same. Okay. So this is the final compressed trie. So let's see what is the maximum height of the initial tree. What will be the height of the tree? 1, the largest prefix. The width of the largest prefix. 1, 2, 3, 4, 5, 6, 7. So 7 is the height of the original trie. Now when we compressed, let's see how much is the height. 1, 2, 3, 4, 5 and 6. So by compressing we could bring it down by 1. So the compressed, so the question was this table was given, okay. This prefix table was given and you were asked to find the height of the trie constructed using a path compressed trie. So given the prefix table, what is the height of the path compressed trie? So to do the path compressed trie, first we have to construct the trie. Then we construct the path compressed trie, and then the height is found out as 6. The options given were 6, 7, 8 and 9. So if we are counting like having one node in the trie as height 1, then it is 1, 2, 3, 4, 5, 6. Or if we are taking like this as one height 1, 2, 3, 4, 5, then it is 5. But in general, it is taken like if there is one node, we consider it of the node of the trie of height 1. So answer is 6 here. Okay. So I think so this is how the question comes, and this was the motivation behind discussing all these things. Hope that is clear. Okay. So now shall we move to the next multi-bit trie? I think okay. In multi-bit trie, how we do is like we saw that in binary trie we were using zeros and ones, so it was a single bit comparison. Whereas in path compressed trie, some places based on the skip length and the segment, sometimes the number of bits we compare will be 1, sometimes 2, sometimes 3, so it's variable. Now in multi-bit trie, here the concept is instead of 1 bit, can we have n bits at each node? Can we do the comparison using n bits? So the n could be 2, 3, 4, 5, etc. So let's take an example and see first how it is done considering 2 bits. So instead of 1 bit, let's see that we do the comparison of 2 bits. Then how this trie gets constructed. Okay. So when we normally in a binary trie we have since we are comparing 1 bit, we have two possibility, a 0 and a 1, right? When we have 2 bits, how many possibilities are there? We have 2 power 2, which is this is 2 power 1 possibility, which is 2. When we are comparing, when we have 2 bits, we have 2 power 2, 4 possibilities. So we can have a 0 0, 0 1, 1 0 and 1 1, right? So these are the, from every node we can have 4 different possibilities, right? If you are taking 3 bits, then 2 power 3, 8 possibilities. So from one node we can have like 8 possible prefix, options 0 0 0, 0 0 1, 0 1 0, 1 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. Okay, so these are the possibilities based on the number of bits that we are choosing. This will be the number of siblings or children the node can have. Okay, let's first take an example and try to construct one and see. Simple example, P1 star, P2 0 0 star, P3 1 1 star, P4 1 1 followed by 1 0 star, P5 is 1 1 1 1 star, P6 1 1 1 1 0 star, P7 1 1 1 0 0 star. So now how will we construct such a trie? Okay, so so every time we compare, we will be comparing 2 bits, right? So there is this wildcard entry possible, and what are the combinations possible with 2 bits? 0 0 0 1 1 0 1 1. At the top node, at the first node, we will be comparing 2 bits, right? So what could be the possible match, or what are the possible prefixes that would match from this? So 0 0 we have this, so 0 0 will match P2, and 1 1 we have P3. 0 1 and 1 0 will match with P1. Okay, now this is the first level. Now from here, when we go down further, now let's take the, so this is done, the first level we have seen. Now the second, since this is 2-bit, right, we will take the multiple of 2s, we will take the prefix lines like that. So this P4, P5, P6 and P7, rest all the prefixes have the initial 1 1. Okay, after that, what are the possible combinations? Let's see again. What are the combinations possible? Again it is 0 0 0 1 1 0 and 1 1 only, right? So 0 0, do we have any prefix like, so this is this one we have to see. Now is there any prefix with 1100? Do we have any prefix with 1100? We don't have any, so this will match to P3 only. Do we have any prefix which is 1101, 1101? We don't have any 1101 also, so that also will be with P3 only. Do we have any with which is 1110, 11 and 10? So this will match with P4. 1111 will match with P5. Okay, now again we will again go to this side. Okay, we have 1110. We have 1110 matching with P4 and this P7. Okay, now next iteration we have again 0 0 0 1 1 0 1 1 in the next set of 2 bits. Okay, so now if we see this is the next prefixes, one is 1110, the other prefix that have what is this called, more than 4 bits is 1111, right? So with 1111 this 0 star is coming, so it can be 0 1, it can match with 0 0 and 0 1. So 0 0 and 0 1 will go for P6, will match with P6. Then this is when it comes from 1 1. Now if it is coming from 1 1 1 1 1 0, then P7 is having again 0 0. Okay, this is little confusing. I will draw the tree, that's would be easier. Okay, so we have initially we have P1 0 0 0 1 1 0 1 1. Okay, of this P2 and P3 is, P2 is, this is P2, this is P3, this will correspond to P1 and P1. Okay, now let us see the so we have so this is the initial starting point, 0 0 0 1 1 0 1 1. Of that 0 0 will match with P2, 1 1 will match with P3, and the other two will match with P1. Okay, now let's see what is the prefix of the other prefix, what is the starting of the other available prefixes. So they are also, they are starting with 1 1 only. Okay, so we will have children for P3. So what could be the we have already seen that we can have 4 different children, right? Again 0 0 0 1 1 0 1 1. prefix, do we have any prefix like 1100 here? 1100 we don't have. Okay, we don't have. 1101 we have. 1101 we don't have. 1110, 1110 we have. This is P4. Now 1110 we have. This one also 1110. Okay. P7 have one more, so we will not write it here. We are currently taking only 4-bit prefixes. So do we have any 1111? Yes, we have 1111. That is P5. Okay. Now, so we have now P4 and P5 here. Now let's see what are the other two. So these are the other two left out, which we are yet to fill in. So this is starting with 1 1 followed by a 0. So 1 1 1 1. Okay, so P6 will take this path, P3 this path. Okay, then it will go to, it can go to 0. There is a 0 here already. This is 1 1 1 1. The 0 is fixed and this is star, which means that it can be 0 0 and 0 1. So P5 will have 0 0 and 0 1, and that corresponds to the prefix P6. Okay. Now for P7 will be 1 1 1 0. So 1 1 1 0. And from here it is also 1 1 1 0 followed by a 0 and a star. Right. So the star can be 0 as well as 1. So 1 1 1 0 0 0 and 1 1 1 0 0 1 both will correspond to P7. So this is again 0 0 0 1. This is P7 and P5. Is this clear? How we are building this multi-bit tree? Try. So now any prefix, if we get any prefix like, so we can put it like this. We can have P1 here, which will match with everyone. Then from P1, we will have 0 0 means it will go here. 1 1, so it will come here. Then if suppose we have a prefix starting with 1 0 1 0, where will it go? 1 0 1 0 will match with P1 only. If we have a prefix starting with 1 1 1 1, if we have an IP address with a prefix starting with 1 1 1 1, we'll see one more example, don't worry. So 1 1 is P3 followed by another, which is the other 1 1, other 1 1 is this one, P5. So this IP address with the prefix 1 1 will match with P5 and will get forwarded to that corresponding port number. It's little confusing. Okay, let's see one more example. Let's see. Let's try. P1 is again we are taking 2-bit comparisons. Okay, so P1 is 1 0 0 0 1 1 star. P2 is 1 0 0 star. P3 is 1 0 0 1 1 1 star. P4 is 1 0 0 1 1 star. So we have 0 0 0 1 1 0 1 1 initially. Okay, so so here in multi-bit drive we normally start from the smaller one. Okay, so P2 if we start, it corresponds to 1 0. Okay, so we have we cannot write P2 here because P2 is 1 0 followed by 0 star, and all of them have this same prefix here. So we will track this particular node. Okay, so this can have again 4 after 10 we can have another 4 combinations. So this is again 0 0 0 1 1 0 1 1. So does any of the does this match, does P2 match with 1 0 0 0? P2 is 1 0 0 star. Okay, the star can be anything, it can be 0 or 1. So when we write 1 0 0 star, it is typically 1 0 0 0 or 1 0 0 1. This is equivalent of 1 0 0 star. Okay, we can consider it like this. So 1 0 0 0 will be P2. Same way 1 0 0 1 will also be P2. Okay, then after that, which is the next smallest one, P4. So let's see where P4 will go to. P4 is 1 0 0 1 followed by 1 star. So P4 is 1 0 0 1. So it is this path 1 0 0 1 1 0 and followed by 0 1 P2. Now there is it is after that the bit that is coming is 1 star. So again a star we will replace it by 1 0 and 1 1. So 1 0 0 1 1 0 1 0 0 1 1 1. This will be P4. So from P2 again we can have 1 2 3 4 0 0 0 1 1 0 1 1. So P4 comes as 1 0 followed by 0 1 followed by 1 0 and 1 1 1 0 and 1 1. So this is P4. So we are done with P4, we are done with P2. Now what is left is now P1. P1 is 1 0 followed by 0 0. So this one followed by another 1 1. So that is P1. So it can have another 3 more, but there is no prefix for those. So we can ignore that as well. Okay. It's like I have drawn these extra lines, but we don't have any corresponding prefixes. Okay. So they will all match with P2. So if I get a prefix like 1 0 0 1 0 0, 1 0 is there, 0 1 1 0 0 1 is P2. After that there is no prefix. So 1 0 0 1 0 0 will match with P2. Same way 1 0 0 1 again 0 1 will also match with P2. But 1 0 0 1 1 0 will match with P4. So this is P1. Now what is left is P3. P3 is 1 0 0 1 and 1 1. So this is more specific, so we keep it as P3. Okay. And we always go for this longest most prefix match, right? So when there was a P3 is more what to say, longer than P4. So when a more longer match came, we replaced that with P3. Okay. So this is how the multi-bit trie is constructed. I mean, did this help you guys understand? Little bit. So it is how it is like it is instead of earlier we were traversing zeros and ones, in place of that typically so that too whenever there is when a 0 comes only we were putting a left child, when a 1 comes we were putting a right child, right? Same way here instead of 0 and 1 we have 4 numbers to check, 0 0 0 1 1 0 and 1 1. It's checked in a lot of 2. So whenever there is a corresponding prefix available, we will make a child accordingly. So here I just made and kept, but actually these are not needed. These are the children, these children are sufficient. So for here I did not make those, all the 4 combinations possible. Maybe to be more clear, so for example, here if you see from P8, here you see P8 say, I'm taking a right because there was a 1. But I didn't mark a 0 and keep it here, right? We didn't do that. We only took those based on the available prefixes. Same way. I didn't mark a 0 and keep it, right, empty. Same way here also. Instead of, the only thing is instead of 2, we have 4 combinations available. Now if we go to 3 bit, we will have 8 different combinations available. Maybe I'll take an example once again, we'll see how it goes, okay? The same way. So this example that I showed, let's see that with 3 bit, okay. So P1 is 100 star, P2 is 100 star, P3 is 100 star, P4 is 100 star. Okay. So which is the smallest 3 bit prefix? It is P2. So we'll start with P2. We'll start with 100. This is P2. And what is the prefix for all the available, for all these prefixes? This the first 3 bits is the same. So we'll start with 100. Okay. So now right. Now from if we see with the same earlier example, there are with 3 bits we can have 7 different, I mean 8 children are possible. Like with 1 bit we can have 2 children, 2 bits we can have 4 children, with 3 bits I can have 8 children, right? So now let's see what are the 8 children possible. 0 0 0 0 0 1. What are the 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, these are the possible next 3 bits combinations possible. Now let us see in the prefix P1 is 100 followed by 0 1 1. So 100 followed by 0 1 1. Where is 0 1 1? 0 1 1 is here. So this becomes 0 1 1. This becomes P1. P3 is 100 followed by 1 1 1. 100 followed by 1 1 1. So this is P3. P4 is 100. We did P2, we did P1, we did P3. Now P4 is 100 followed by 1 star. When we are going for 3 bit comparisons, no, this star, we have to always push the star to this. This is star, but here we need to replace it. We need to have proper bits. So this will be, this star can be replaced by 110 and 111. Okay. So when we are doing multi-bit try, based on that k bits should we have to expand it. That star needs to be expanded. If it is coming in that two bit position, it has to be expanded. Okay. So that's what we have done here. So this star I have expanded it to 0 and 1. Now if we see P4 is 100 followed by 110. 100 followed by 110. This is P4. 100 followed by 111. Already P3 is there, which is more, which is even a longer match. So we will not change it. P3 will continue there. P4 will be 100 followed by 110. P1 is 100 followed by 011. So the prefix trie would look like P2 011 P1, then 11 1. Sure. That one. Oh no. So somehow that got erased. So I'll just quickly write how the try looks like. It is for the prefix, so that you will understand. Like that if you refer to it. So 3-bit. P1 is 100 star. P2 is 100 star. P3 is 100 star. P4 is 100 star. So the try will look like P2, which is 100, then P1, 0 1 1, then P3, which is 111, and P4, which is 110. So this is how the multi-bit try for the given prefix would look like. Okay. Okay, now I'll take another question from the previous year question paper. You can unmute and speak. Okay.
Me.
This question from last year's assignment is from the hardware based try. Okay. So in the DIR 24/8 mechanism, how the prefixes are stored, and based on that, there was a question. Okay, so I will just quickly it's already go through that. So I think you all know, right? In this DIR 24/8 representation, the prefixes will be stored in two levels, right? In the first level, all the prefix from having length from 0 to 23 will be stored, and the prefixes having prefix length greater will be stored in the second level. This is the first level, and this is the second level. So there is a bit which will help identify whether it is in the first level or the second level. So if that bit is set to 1, it implies that it's a longer prefix. It has the prefix longer than 24. So we have to go to the second level and retrieve the prefix. Okay. So now and the example here is, consider the scenario wherein DIR 24/8 algorithm performs route lookup using two tables. Assume the routes listed below are already in the table, like 10.54/16. This is the next hop one. 10.54.34/24. This is next hop 2, and 10.54.34.192/26. This is next hop 3. This is already in the table, okay, hardware table. The first route, the question is, the first route requires entries in TLB 24, while the second and third require entries in the second table. Which of the statement is correct is the question. So how was this representation done? So in DIR, in the first, what will all the we have told that 0 to 23, whichever prefixes have their length from 0 to 24, they will have the matching route available in the first level. So for a 24, so 2 power 24 entries will be there in the first level. Okay, and corresponding to each entry in the first level, there will be 256 different entries in the second level. If we have a higher prefix length. Okay, so in this given scenario, we have 10.54 points /16. So 16, this mask is definitely less than 24. So it will be available in the first table itself. So what will happen is, in the table, how the entries will be, all 2 power 24 entries will be there. So if we take this 10.54 point this, okay, this can vary from 0 to 256, right? And all all these entries will be there. So 10.54.0 to 0, 10.54.1, 10.54.2, like that, 10.54.255 will be in the first level. Okay, so now the question is 10.54.22.147. Where will this be present? This IP address be present? Whether it will be in the first table or in the second table.
I'm sending in WhatsApp, bro. In WhatsApp. I didn't have the Why?
Okay, so this 54.22.147, this will be falling since we don't have, there is no prefix which have more than 24 length for the standard 54.22 given. This will match from the first table itself. So somewhere here we will have a 10.54.22. Okay, so this will go to next hop one itself. So it will match in the first table. Whereas for 10.54 for 34, since the mask is 24, this will have a corresponding 256 entries in the second table. 10.54.34.0, 10.54.34.1, like that. We will have 10.54.34.192, 10.54.34.193, like that, 10.54.34.255. So this particular entry will have these many corresponding entries in the second level table. So if I have an IP address like 10.54.34.23, the question is which next hop will this IP get forwarded? So since this will come here, it will see 10.54.34 and the bit will be set to 1 because this mask is greater than 24. It will go to the second table. In the second table, we will have 34.23 somewhere here. 10.54.34.23 with next hop has 2. Okay, so this will get forwarded to, for this packet it will use this particular entry and get forwarded to port number 2. Now the next one is 10.54.34.15. 10.54.34.15. Where will the entry be? It will hit the entry in the first table or the second table?
Second table, ma'am.
Second table, right? So here again, somewhere here there will be another entry dot 15 and it will also have a next hop of 2. Now the last one is 10.54.39.128. Where will this entry be?
First table, ma'am.
Second table, ma'am.
It will be in the first table because only 34 has a prefix of 26 given. Okay, 26 and 24 given. For 39, there is no more specific prefix given, so it will fall under this category 10.54/16. So 34, 35, 36, somewhere here 39 will come. So it will be in the first table and it will be forwarded to the next hop 1. Okay, this is clear. If you have any doubt, let me know. I'll try to explain it again. All right. Then I will go to the MCQ questions from previous year. Okay. Screen is visible, right?
No.
Not visible.
Ma'am, actually screen is visible for me.
All right, so could be some network issue. Others?
Screen is visible, ma'am.
Right, okay, thanks. So I will quickly, there were a couple of MCQ questions and few of the problems I have in between solved, okay? So the first one is, which among the following is true when the trie constructed with a set of prefixes results in a full binary tree, okay? So when we have a full binary tree, only a binary tree trie has the best lookup and update complexity. So the question is, which of the following is true? Only path compressed trie has the best lookup and update complexity. Both binary and path compressed trie have the same lookup and update complexity. Binary trie and path compressed tries have the same lookup complexity but different update complexity. So we have already seen that one of the criteria for path compression is that the intermediate node should not have two children, right? So when it is a full trie, when it is a complete trie, it means that all the intermediate nodes have two children, which means that path compression will not be possible. Okay, so a full binary trie, we cannot do a path compression. So even if we try to do, we will not be able to reduce anything. So a path compressed trie and a full binary trie will be the same only. So because of which both of them will have the same lookup and update complexity. So the answer is C here, okay. So given a routing table having
Hello,
given a, yeah.
ma'am. Can you know about the space complexity of the previous question?
Space complexity also will be it will be the same only because we won't be doing any path compression itself, right? So we won't be adding the skip length or the segment information. So space complexity for a full binary trie, the space complexity for that trie and its corresponding path compressed trie will be the same because we won't be able to do any path compression there. Typically, the path compressed trie and it will be the same actually.
Okay.
You understood, right? Like the criteria for compressing is that the intermediate node should have only one child. All of you know this notion of binary trie, right? I mean full binary trie. Full trie means all the intermediate node, every node in the tree will have two children. So in such a scenario, path compression will not be possible at all. So both will be the same, hence the update, lookup, space complexity, everything will be the same. I think I just explained, I guess. So the answer for the first question is C. Okay, so basically, I think someone missed that discussion. Basically, a path compressed trie. The question is given a full binary tree. which of the following is true. Okay, so the option is C, because given a full binary trie, if we try, we first of all we will not be able to do any path compression on it, because all the nodes will be having 2 children. So even if we tell that we have done path compression, the path compressed trie of a full binary trie will be the same. Hence, all the lookup update and all the complexity will be the same, because both will be the same only. Now, question number 2, given a routing table having 5 prefixes with prefix length 0, 2, 4, 6 and 8 respectively, pointer references are required in the worst case for the binary tries. How many pointer references are required in the worst case? That is the question. Okay, so the number of references required will be equivalent, worst case scenario will be equivalent to the maximum prefix length. So here 5 prefixes are given, and the length of the prefixes are 0, 2, 4, 6 and 8. So what is the maximum prefix length here?
It's at
Maximum prefix length here given is 6. I think I'll have the other, I'll write and explain, I guess. Will that be better?
yes, ma'am.
Okay, I'll share. Probably I'll read out this question and then I'll share from here. So yeah, just a quick, this is what is a full binary tree is, okay. So on such a tree, we cannot do path compression. Those who are having doubt. We can do path compression on trees like this. Okay. Maybe in between one or two nodes, if we have also, it's okay. Such trees we can do path compression. In here, we can't do any path compression. Now here what is given is we have some P1, P2, P3, P4 and P5 with length 2 and 0, 2, 4, 6 and 8. 0 means it is star. 2 means some X, Y star. This is X, Y, P, Q star. Same way. 1, 2, 1, 2, 3, 4, 5, 6 star. 1, 2, 3, 4, 5, 6, 7, 8 star. So this is what length 8 means. So it will have 8 bits here. If we have this prefix have 6. If we have such a prefix, what will be the number of worst case references required? Okay. So if randomly, let's assume this prefix is 1, 0, 1, 0, 1, 0, 1, 0. Then if we construct the trie, it is 1, 0, 1, 0, 1, 0, 1, 0. 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and this is P5. And if we assume this as 1, 1, 0, 0, 0, 0, 1, some random number, okay, no issues, anything can be thought of. 1, 2, 3, 4, and 5. 0, 0, 0, 0, 1. This is P6. Okay, now tell me how many comparisons do we need? If I have an IP address which is matching with P5, how many comparisons will I have to do? I will do a comparison here. I'll do a comparison here. One here, 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 right? So it will be equal to the how many references I will take. I'll have a comparison here. I'll take a reference here. I'll have a comparison, I'll go here. I'll have a comparison, I will do a pointer reference here. compare, refer, compare, refer, compare, refer, compare, refer. Finally, we'll reach here. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. Right? For P6, it will be 6. For 4, it will be 4. So this number of pointer reference required in the worst case will be equal to the longest prefix length. Okay. So the answer here will be 8 only. Is this clear?
Yes, ma'am.
Next question. Yeah, it's a different this one. In which case will a path compressed trie resemble a regular binary trie? When will a path compressed trie resemble a regular binary trie? We just discussed in the first question. When the trie is full. Okay, the options are when the trie is sparse, when the trie is dense, when the trie is almost complete, when the trie is full. So the last option is the correct one. When the trie is full, that is the scenario. When the trie is full, a path compressed trie will resemble a regular binary trie. Okay. Now, and the other question is, right, consider the prefix database table shown below. What is the height of the trie constructed using a 1-bit binary trie? I think we did this. Yeah, this question. So this was the prefix given, and the question is what is the height of the trie constructed using a 1-bit binary trie? So this is the trie constructed using a 1-bit binary trie, and the question is what is the height of this trie? The height will be the 1. We will see the longest prefix, which is P9, and we will see the number of nodes traversed in P9. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the height of this trie is 8. Okay, then the second question is again that we just discussed here. The same trie given, consider the prefix database shown here, the same database they gave, and what is the height of the path compressed trie. So we had from this one we have computed the path compressed trie, and we found that the height is 6. Right, we found that 1, 2, 3, 4, 5, 6. 6 is the height of the path compressed trie. But for the regular trie, what was the height? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So I'm not doing it again. We have already done it. The next question is given a prefix table. Oops. P2 0 star, P3 is 1 1 star, P4 is 1 0 0 star, P5 is 1 0 1 0 star. Okay, so this is the prefix given. The question is what is the lookup sequence to reach destination address 101000000. So here we have P1, we have P2, then we have P3, 1, Then we have P4, 1, 0, 0. Then we have P5, 1, 0, 1, 0. Okay, so what is the destination is 1, 0, 1, 1, 0, 1, 0. So this is what is being traversed, P1 to P5. So this destination will match with P5. So what they are asking is, what is the traversal sequence? Is it right, left, left, right, right, left, right, 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 left, right, left, left, right, left, right. So this is right, left, right, left. Correct. So the answer is right, left, right, followed by left. Okay, oh, this is clear, I think, right? Yeah. The other question we just discussed. The last one is which of the following statements is correct? Path compress trie is an efficient way to compress a trie when nodes are sparsely populated. Okay, so that is correct. When nodes are sparsely populated, that is when it is not dense, when the trie is not complete, when intermediate nodes does not have two children, that is when it is sparsely populated. Path compress trie is an efficient way to compress the trie. So that is true. Level compression trie is an efficient way to compress a trie when the nodes are densely populated. Yes, so level compression is a technique that we use when the trie is almost enough complete or full kind of a trie. So that is when we use a level compression trie. I think we didn't see the examples of it. So level compression trie is the efficient way to compress a trie when the nodes are densely populated. That is also true. A path compress trie is an efficient way to compress a trie when the nodes are densely populated. That is wrong. We cannot do path compression when the trie is when the nodes are densely populated. That is when majority of the nodes have two children, then we cannot do path compression. So the statement is false. Multi-bit trie can improve route lookup performance. That is also true. Multi-bit trie reduces the number of references required by the number of bits. So, for example, if you are using a 3-bit or a k-bit trie, it will reduce the number of references by k. So that improves the route lookup performance. Okay, so that was one, and yeah, one more is there. So which of the statements about the hardware-based routing lookup algorithm is correct? So if the length of the prefix P is less than 25 bits, so I have told that if it is 0 to 24, the bit will be set to 0. And if it is 24 to 32, the first bit will be set to 1, which indicates that you have to go to the second level. Okay, now have this in mind. If the length of the prefix is less than, prefix length is less than 25, first bit of the entry is set to 1. So which is correct is what it is asking, okay? First bit set to 1. The next one is if the length of the prefix is less than 25, prefix length is less than 25, first bit set to 0. Prefix length is greater than 24. First bit is 1. The last option is prefix length is greater than 24. First bit is 0. So which of them are correct here? So this is the how it is. 0 to 24 means it is 0, and 24 to 32 it is 1.
Third option is correct.
Third is correct. Second, length is less than 25 is nothing but 0 to 24, no? So this is also correct. Okay. So these two options are correct here. So I will be putting all this material. I'll share my drive link, okay, so that you guys can take a look at the slides if needed. I'll be putting, but video link, I don't know how I can share. I can share the last session's video now, but give me a minute. Mm, 50 drive, okay. So in this drive, the PPT, this handwritten notes will be uploaded that you can refer. The video link, I don't have it now because I'll be uploading it after that only, no? What I can do is, yeah, previous sessions video, this is it. Or you can check the channel, right? YouTube channel. I will be uploading it in my YouTube channel. You can check that. There, I normally upload it in another 1 or 2 days time. By Monday mostly I'll be uploading the video. So by Monday you'll be able to get that. So maybe I can share the channel. Just, I think just try search with my name Ranjita K, or this should be the ID, I think. Just try. I started it, I think, for last some NPTEL course. So just try with my name. Yeah, so last session video will be there. The session I'll be uploading mostly by Monday. Okay, so you can check it out. So I mean, I just want to know, is this format of session fine? Are you able to follow, or do you want me to go through the content as explained by the professor, or just problem solving is good? You're not able to open the folder. Can someone else try once and let me know if the given permission correctly only?
Ma'am, I can open the folder.
Oh, okay, then I think it's
Yeah.
And ma'am, answer to your question, that content is also good, ma'am. Like how you're explaining like content and then the problem solving, it's good for us.
So you prefer to have a quick summary of the content
Yes,
rather
yes.
than directly going for the problems.
Yes, ma'am. With some background, like it will be easy to understand.
Sure, sure, yeah. Yeah. So I was thinking like already the lectures are there, no? So why to repeat it? Okay, I get it. I'll try to summarize maybe in a half an hour time. Take half an hour in the initial start of the session, summarize quickly, and then get into the problems.
Okay.
Okay,
Okay, ma'am. Thanks, ma'am.
right. Yeah. It shows unable to access the document. Are you all able to access? Can someone just quickly open one of that last PDF and check once?
Ma'am, PDFs can able to open? Yes, ma'am. It's openable.
Okay, okay. It should be some issue probably. Maybe you log in and try. Log in with Gmail and try. I don't know. I have set it like with the link, you should be able to open it. All right. Any other queries, questions? Otherwise, we can wind up the session. Right. So I guess no more queries, questions. Thank you so much. We'll have the again one more session will be there on Tuesday. Another scholar will be taking that. Again, I'll be having this similar sessions every Friday 6 to 8. So see you next class. Bye bye. Good night. Thank you.
Okay. Bye.
Thank you, ma'am.